If you haven't done so yet, please pause the video and try to answer the question yourself before listening on. In order to calculate the magnitude and direction of the net electrostatic force on particle 4, we have to consider the equation that relates the electrostatic force exerted between two charged particles, which is also known as Coulomb's law. So let's take a look at that equation. In that equation, the electrostatic force is equal to a constant multiplied by the magnitude of the two charges divided by the distance between the charges squared. Now, it's going to be worth signifying whether the charges in the diagram are positive or negative, and that will be based on the given information. For example, charge 1, Q1, is stated to be negative. So we'll go ahead and put a negative sign beside that charge. Q2 and Q3 and Q4 are all positive, so we can put positive signs next to those charges. Now, looking at charge 2 and charge 4, because they are both positive, we know that the force between those two charges will be a repulsive force. And so charge 4 is going to be pushed away from charge 2. And so we would have a force that we could label F24 pointed in this direction. The force between charge 4 and charge 1 is an attractive force because the signs of the charges are opposing. And so charge 4 is actually going to be pulled towards charge 1. And so we can label a second force as F14. And finally, charge 4 and charge 3, because they're both positive, are exerting another repulsive force. And so that means charge 4 is going to be pushed away from charge 3 along the negative x-axis, and so we can label that force F34. Now, using Coulomb's law, we're going to have to make three calculations. One for the force that 2 exerts on 4, another for the force that 1 exerts on 4, and a third for the force that 3 exerts on 4. Now, we're actually going to want to set up a little table here so that we can distinguish between the x component of the forces as well as the y component of the forces. Now, F24, because it's projecting along the y-axis, actually has a y component but no x component. And so we're going to put 0 newtons for the x component of F24. For the y component, we'll end up using Coulomb's law. Notice that we're using charge 2 and charge 4 for this force, and that the distance between the two charges is d2, as shown in the diagram. Now, keep in mind that that force is pointing downward, and so we have to assign a negative sign to that y component force because of the downward direction. Moving on to F14, we're once again going to use Coulomb's law, but we have to break this into both an x and a y component. And to do that, we would have to figure out the angle that that force is pointing at. Now, traditionally, angles are measured from the positive x-axis. So if we look carefully, what we want is this angle right here. Now, theta 1 was stated in the question to be 35 degrees. So that means when we measure from the positive x-axis all the way to this force marked F14, we're going to add 180 degrees plus the 35 degrees for a total angle of 210 degrees. So that would be the entire angle that we'll use for the x and the y component. Remember that for the x component, we use the cosine of that angle. So we'll have cosine of 210. And then for the y component, we'll have the sine of that angle. And then we'll have to fill in the Coulomb's law expression for that force using this equation. So notice in this case, we're using charge Q1 and Q4 in the calculation, and the distance between those two charges is marked in the diagram as d1. So we've used that as the distance. For the final force, F34, we can see that it's pointing exactly along the x-axis. That means the y component is going to have a value of 0 newtons. And then because that force is pointing along the negative x-axis, we have to include a negative sign for its force. And then we'll fill in the corresponding Coulomb's law expression. Notice we're using charge Q3 and Q4 for the force acting between those two charges. And also notice that the distance between those two charges is represented by d3. So now what we want to do is pick up our calculators and plug in all the known values for Q1, Q2, Q3, Q4, as well as the distances. Now, your distances have to be converted into meters, and so you'll have to multiply each one by 10 to the minus 2. So d1 would be 3 times 10 to the minus 2. d2 and d3 will both be 2 times 10 to the minus 2. So pick up your calculator and carefully plug in each of these 4 expressions so we can simplify. Now, hopefully when you simplify those on your calculator, you have the following 4 values. What we want to do next is add together the 3 x components to get a total x component, and then also add together the 3 y components to get a total y component. So let's pick up our calculators again and basically add vertically downward to get the total x, and then vertically downward to get the total y. And when we do so, we get this value for the total x component and this value for the total y component. Next, what we want to do is take those 2 components and draw them on a new set of coordinate axes. Now, because the total x component has a negative value, that means it will be projecting along the negative x axis. So we could point a vector in this direction. And similarly, the y component has a negative sign, so it too will be projecting along the negative axis, but this time it'll be the negative y axis. So in other words, we'll have a vector pointing straight down. So those would be the 2 components of the resultant force. The actual resultant force would simply be the vector sum. So we would have the resultant pointing in this fashion right here. And it is our job to find that resultant. And to do that, we can use the Pythagorean theorem. So with the x and y components labeled, we'll go ahead and set up the Pythagorean theorem down here. And then we'll take the square root of both sides of this computation to give us our final magnitude for the net force. And when we do that, we should get approximately 6.17 times 10 to the minus 24 newtons as the final magnitude of the net force acting on charged force. So that will be the correct answer to part A. For the direction, what we need to do is actually figure out this angle right here, which we can mark theta. And we know that the tangent of theta would equal the opposite side of this right triangle divided by the adjacent. Now the opposite side is the 2.81 times 10 to the minus 24, and the adjacent is the 5.49 times 10 to the minus 24. Since they're both times 10 to the minus 24, we can actually drop that part of the numbers, and so we'll have just 2.81 divided by 5.49, and then we'll have to take the inverse tangent to get the actual angle. And that turns out to be roughly 27.1 degrees. Now that's this angle here. Usually a physics problem wants you to state the angle relative to the positive x-axis. So if we measured the angle from that axis all the way to our resultant, we would have to take 180 degrees right here and add that to the 27.1 that we just found. So overall, the angle should be approximately 207.1 degrees, and that would be measured counterclockwise from the positive x-axis. And so that would be the final answer to part B of the question. Thanks for watching. If you liked the video, please click the thumbs up and also subscribe. Remember, you can send in your own question to the email address on the screen, and I'll do my best to respond to it on YouTube.